2 of extremes, definition 3 of extremes. Alright, the next. So today we're going to start on something entirely different, which is called portfolio theory. Oh, you can't see it. Sure. Can you see it now? It's called portfolio theory, right? So this section of the course is more to do with financial risk than extreme value. As I said in the beginning, there are 2 parts to this course. One is extreme values, and the second part is financial risk. So this part of the course is more to do with financial risk than extreme values. So far, everything we talked about is about extreme values. So this is okay. All right, guys. So just a minute. Right. A portfolio, I'm sure all of you know what a portfolio is. A portfolio is a collection of investments. So for example, investment on gold, silver and copper, that could be a portfolio, right? Or investment on different kind of properties, that could be another investment. So that could be a portfolio, right? Okay, so these are 2 examples of portfolios, right? So now I'm going to introduce some notation. Let n denote the number of investments in the portfolio, right? And let So here n denotes the number of investments in a portfolio, right? So for example, in the first example, the number of investments is 3, right? Because you have 3 different commodities, so 3 different investments. And let x1 denote the loss on investment 1, x2 the loss on investment 2, up to xn the loss on investment n. So you have these variables x1 to xn, right? Okay. Now let me put it here. Hopefully you can see this. Can you see this? No? No? Can you see this one? Yes. No, I can't see it. Why? Maybe. Can you see it now? Yes? Okay. Okay. Alright. Okay, now sorry. There can be 6 possible cases, right? Case 1, I mean, when I say 6 possible cases, they all relate to the investment, the loss in investments, x1 to xn. Case 1 is that the losses are independent and are identically distributed, and n is fixed, right? Case 2, that the losses are independent and identically distributed, and n is itself a random variable, right? Case 3, I and ID means the following. I'll explain in a minute what it means. It means right. So I and ID means that they are independent but not identically distributed, right? But n is fixed, right? So that's case 3. Case 4, okay, that's case 4. Case 5, fixed. And case 6, alright, so these are the six cases that are possible in practice, right? I'll put it here. Hopefully you can see this. Sorry. Alright, so hopefully you can see it. So these are the 6 possible cases that can arise in practice, right? You understand? Okay. So the most practical of these 6 steps is case 5, where the losses in the n investments are dependent random variables and n is fixed. So this is the most realistic of all the 6 cases, right? Because normally, like when you have investments on different commodities or different properties, you would expect the losses to be dependent on each other, not independent, right? You understand? Okay. So case number 5 is the most realistic of all the 6. Well, anyway, we will consider each of the 6 cases in turn. Oh. We just started working on portfolio theory. We just started with portfolio theory. Yeah. All right. The next thing now, the next thing we need to ask ourselves is, what are the variables of interest? We have this n investments, right? We have the n investment and we have the n losses. So x1 to xn are the losses. Now the question is, what are the? There are 3 variables of interest. Part A is this one. Now what is this? I'm summing all the losses. So what is it known as? This is known as the total portfolio loss, right? Remember, x1 to xn are the losses on the n investments, right? So if you sum them, you get the total portfolio loss, right? Okay. Part B So this is the minimum portfolio loss. In other words, you have this n investments, and what this gives you is the investment that is least expensive, or the least most profitable. In other words, I mean, when you say the least loss, that means it's the one that worth keeping, the investment that is worth keeping, right? Okay, so that's the least of the losses, right, or the smallest of the losses. Finally, V is the maximum portfolio loss. In other words, this will tell you the investment that is the most costly. So you like to get rid of that investment, right? Because it is the most costly of the end investments. All right. All right, guys. So these are three variables of interest as far as portfolios. I mean, there are others also, of course. But I mean, for this course, I will only focus on these three variables. Okay. Any questions so far, guys? Yes? No? Okay. Let me know if you. I mean, feel free to. Any questions you have, just feel free to ask. Okay. Oh, feel free to ask. Before I go ahead, I forgot the chocolates. I brought some chocolates. You guys could come for chocolate. How are you? I saw your friend outside, but I don't know if he's okay. All right. Now, what I'm going to do is I'm going to go through the 6 cases. So the first case is case 1. So case 1 is that just to remind you that x1 to xn are IID and n is fixed. Okay, this is case 1. Okay. Now I'm gonna show you how to actually derive. Well, you don't need to know how to derive. How to write down the probability distributions of these 3 variables of interest, S, U, and V. Right. So starting with S. The CDF of S is this, which is the probability that capital S is less than or equal to little s, right? Okay. Okay, and this you can write as follows. when I write an integral, I'm assuming that all the variables are continuous. I mean, if the variables are not continuous, then you need to replace this by sum, right? Okay, so I'm assuming that they are continuous, right? Just give me a sec. Um, Right, and the integral is over the region that with the sum I from 1 to n of xi is less than or equal to s, right? So do you follow what I've done, right? So to find the probability that capital S is less than or equal to little s, you just need to integrate the product because the variables are independent, right? Identical. You can write it like this, right? And you need to integrate over n variables over the region that the sum of xi is less than or equal to s, right? Okay, so now you can actually, because they are also identical, you can write it as right. That's because this step follows because of because they are identically distributed. Sorry. Okay, guys, are you with me? Because remember, x1 we are assuming that x1 to xn are IID, which means that the fx1, fx2, and fxn are all of the same form. They all take the same form. So you can write this in this form, where x is the common variable, right? Okay. Let me know if you. I mean, I don't expect you to derive these formulas. I mean, as far as the exam is concerned, I would expect you to know how to apply this, right? Not be able to derive them in the exam. Okay. And the PDF of S, which is written by this, is simply the derivative of the CDF of S. I mean, Obviously you know that, right? Okay, is that clear, guys? Okay. If anything not clear, please let me know. Now I just want to do one example or maybe two examples. I know some of you said I'm not doing enough examples, maybe. So example one, right? Suppose n equal to 2. That means the number of investments is equal to 2, right? So in this case, it's this, right? Now this, if you use this formula here, I don't know if you can see this here. If you use this formula, this would be right. Do you follow what I've done? I've used this. I've used this is the formula when you have n investments, right? Yeah. So if n equals 2, right? This one will look like this, right? It will look like this. Okay. Right. So what this means is that you can simplify this a little bit. If x1 plus x2 is less than or equal to x, what does that mean? It means that right, it means that if x1 goes from minus to plus infinity, x2 has to go from minus infinity to s minus x1. Yeah? You understand or not? If you don't, please let me know. But then this integral here, you should look at this. You should look at this. The thing I have. What you have here is the integral of this density from minus infinity to s minus x1, which is what? Which is okay. Is that clear, guys? Or no? Because when you integrate, this is the PDF of x2, right? So you're integrating the PDF of x2 from minus infinity to this. So what you get is the CDF of x2 at s minus x1. Okay? Right? And And finally, because these are identically distributed, right, you can write it right. So the final step follows because of the fact that x1 and x2 have the same distribution, right? So you could replace x1 and x2 by x, right? Okay. And okay, so this is the CDF of S, right? Now to find the PDF of S, you just need to differentiate the CDF with respect to S, which is okay. So if you differentiate this, you get okay. All right, guys. So this is the formula for the PDF, the density function of S when n equal to 2. Okay. All right. Any questions so far? Sure. Okay. So that's example 1. You could do as an example. I think I will move on. Maybe we can do another example later on. I mean, I think I will try to do another example later. Okay. So now let's move on to B. Remember, B is the minimum portfolio loss, right? So the CDF of U is the probability that is less than or equal to U. Okay. Okay. Now this you can write as the probability that the minimum of x1 to xn is less than or equal to U. Okay. And this you can write as 1 minus the probability. You see why I'm doing this in a minute, right? Okay. And this you can write as, now let me ask you, if the minimum is greater than U, what can you say about each of these? Each has to be greater, right? So it's the same as saying that it's the same as saying this, okay? Is that clear, guys? Okay. Now this is this is because of independence. And we are assuming that x1 to xn are IID, which includes independence, right? Okay. Now, this would become 1 minus, you can write this as 1 minus the probability that x1 okay, and this is, you can write as 1 minus f x1 at u up to 1 minus f xn at u, right? And finally, because these are identically distributed, this is the same as, let me write it down first. This is the same as 1 minus f x u power n. That's because of identical. We are assuming that all of them are identically distributed. So that means each of these must be the same, right? Okay, so that's the CDF of U, and the PDF of U. The PDF is simply the derivative of this. So right? So this is the density function of U. Okay. All right. Any questions on this? Yeah. Yes. No. Let me know, guys. If you have any questions, feel free to ask. All right. All right. Now, next thing, there's no need to do any examples on this because it's trivial. Number is part B. Part C. Part C is the maximum portfolio loss. So what we are looking for is the CDF of V right? Remember, V represents the maximum loss. Okay, so okay. Now, if the maximum is less than or equal to V, then it implies that each of these x's has to be less than or equal to V. Okay. So this would be the same as saying that x1 is less than or equal to V up to xn is less than or equal to V. All right. Now, because of independence, you can write this as this is using is by independence. Right. Now this you can write as fx1 at v, and so on, and this you can write as fxn at v. Right, and this you can write as fx at v power n. That's because the reason for this is because by the identical assumption. Okay, so this is the formula for the CDF of maximum portfolio loss. Right, now the PDF is easy. So you should differentiate this with respect to V. This is what you get. Okay, so this is the density function. Okay, density function of maximum portfolio loss. Okay, any questions so far, guys? You sure? Yeah. Alright, so we covered case 1. Before I go ahead, I want to do some more examples. I only did one example so far. So let me do maybe more examples. Okay. So let's start with example 2. Okay, suppose suppose x1 to xn are IID with normal distribution with mean mu and variance sigma squared, right? Okay, the question is to find the distributions of S, U, and V. I mean, you may get questions like this in the exam. So, but I mean, obviously, to do these kind of questions, you need to know the formulas. But the formulas will be given to you. All you need to do is to apply them, right? Apply the formulas, and derive what the distributions of S, U, and V are, right? Okay. Okay, so let's start with S, for example, which is A, right? A. S is the distribution of what? S is what? X1. S is the sum of, is the total portfolio loss, right? So I know this is where the statistical methods comes in. I know most of you haven't done my course. I used to teach a course called Statistical Methods. You took that, right? I used to teach a course called, that's where do you know what the distribution of x1 to xn is? The sum of x1 to xn? Hmm? No? Oh, come on, guys. Is it like when you have IID normal, what distribution the sum has? Hmm? It will have. It's a well-known result. Is this will have a normal distribution with parameters n mu and n sigma squared. Do you know this result? Yes? Yeah. Okay, that's because that's a property of the normal distribution. If you have x1 to xn IID normal, then the sum is also normal. These parameters. So the CDF of S Alright, so because the distribution of the sum is equal to this, the CDF must take this form, right? Remember, the CDF of a normal distribution is phi. Phi is the CDF of the standard normal time S is the argument minus the mean. In this case, the mean is n mu divided by the square root of the variance, which is square root of n times sigma. Right? That's the formula. I'm sure you know that. If you've done my course, Statistical Methods, you will know this. I mean, if you want to look at I think I gave you a link for my course, which I taught about 2 years ago. So if you want to look at the course notes for Statistical Methods, just follow the link. Do you have the link with you or not? I sent you a long time ago. When I started this course, I sent you a link, a web link for the Statistical Methods. Right, so if you want to look at what I've done, you can look at the link. Okay. And the PDF of S is the derivative of that, which is is 1 over here little phi denotes the PDF of the standard normal, right? In other words, you can write it like this. You can write it like Okay. Okay, so the little phi here. So let me write it down in case you forgot where. Right, guys? Is that clear or not? You have questions? Do you know how I got this? You just finding the derivative of the CDF, you get this. So if you differentiate what I wrote down above, you should differentiate this with respect to S, you will get this, right? And this is equal to this because phi, little phi is the PDF of the standard normal. I'm sure all of you know what the formula is for little phi. Yeah. Any questions, guys? Yeah, Leah, you okay? You sure?
So why the variance is incidence?
What?
Why the variance is incidence is about?
The variance is n sigma squared, yeah.
Why is n times sigma squared?
Because you have n variables, man. You have n. S is the sum of x1 up to xn, right? So when you take the variance of S, it will be the sum of the variances of the x's. So each of the variable has variance sigma squared, and you have n of them, right? So the variance of S will be n sigma squared. Is that clear or not? Some of you look confused. Are you okay, ma'am? You okay? Are you clear with this? Okay. If it's not clear, let me know, guys. Okay. So this is the PDF of S, and this is the CDF of S, right? Okay. So let me put this here. Let me put this here, guys. The next thing is part B. Okay, part B is to find the CDF of U. The CDF of U is gonna be. If you remember the formula that I gave you earlier, this one FU is 1 minus the CDF of X, which is capital phi U minus mu divided by sigma power n. This is the CDF of U. Alright? And the PDF of U do you guys see where this is coming from, guys? Let me show you in case you forgot. This is the formula that I'm using. This formula here. I'm using this guy here to get this, right? And to get the PDF, I'm using this formula here. So you get just the derivative of this, which is n right, and you should differentiate this. You get multiplied by 1 over sigma times little phi U minus mu divided by sigma. So I'm using this formula here to get this formula. Right, now C, the CDF of V Okay, to find the CDF of V, I'm going to use the following formula, which I gave you some time ago. Let me show you guys. This is the formula I'm going to use. This one here. Alright, I'm going to use this one to find the CDF of V. It's going to be if you use this formula, you get 5 of V minus mu divided by sigma everything power n, right, using this formula here, right? And the PDF of V is just the derivative of this. Using this formula here, you get the following. You get okay. So this what I wrote in here is the derivative of this one with respect to V. Okay. Alright guys, so that's example 2. I will take a break. After the break I will do another example, and then it's 5 o'clock now. So let's take a break for 10 minutes. You guys have questions on this? You can ask me. You can ask me now. Okay. You have questions? Yeah. The variances are added, yes. When you have like sum of variables, the variances are added. Yeah. And you have like this. You don't know, like, can I use this one? Like, when you have like, okay, you have say x equal to say x1 plus x2, right? Then the variance of x1, the variance of s, because they are independent, the same as the variance of x1 plus the variance of x2. No, that's how you work on variance. You have questions? Alright guys, you have questions? What about you guys? Do you have any questions? Continuous random variable, like normal distribution is a continuous random variable. Like binomial is discrete, normal is continuous. There are 2 types of random variables, continuous and discrete. Like Poisson distribution is a discrete random variable. Normal distribution is continuous. Exponential is continuous. Yeah, this is the f little fx. Yeah, it's the same as this one. Now you should look at the normal distribution. The density of the normal distribution is this one. You should write down, do you know the density of the normal distribution? Yeah. parameters p and sigma is this one. Yeah. Square root 2 pi times sigma. You know, like no, I think you're confusing. I mean, what you have here is this density of normal. Like, can I use the pen? Like this, like 1 over sigma times this one. Yeah, but this one is the same as the density of the normal. What about you guys? Questions? Yes? Well, come again. Yes, what's the problem? Yeah. Yeah. Which is n times sigma squared. Because x1, remember, variance of x1 is sigma squared. Right?
But if it is variance of n times x1, then it's n squared.
No, I think you're not doing it correct. It's like this. You have s equal to x1 xn. Alright, so the variance of x is equal to variance of x1 up to variance of xn. Okay? Do you understand? Can you see this? Yeah, and this is sigma squared. And this is also sigma squared. So what you have is n times sigma squared. Yeah. Yeah, they're independent, yes. Because they are independent. Yeah. That's how you find. Because you can only do this if they are independent, otherwise you can't do it. Yeah. You can't write x1. You can't write x1 plus xn as n times x. That's not allowed. You can't do it. No. Because yeah, but that's not the same as n times x. You can't write it as n times x. Have you have any other questions? Any questions you have? Alright, you should differentiate the CDF, the second term. You should differentiate the second term with respect to S. You get the PDF. That's what I have done. You should differentiate this. This is the only term is it on S, depends on S. So you should differentiate this with respect to S. You get this.
But it's about
Well, there's not. It's only we are only differentiating with respect to S, not x1. I know what you're saying. same as d by d x minus x1. Yeah. Times ds minus x1 by dx. This is the chain rule. You know the chain rule. That's what it, and this guy here is equal to 1. Right? This is 1, okay? So and this here is equal to little f x s minus x1. So that's how I wrote down. You understand now or no? Still don't understand? I just simply use the chain rule. Although I didn't explain it, but I thought you would understand anyway. I used the chain rule to get from that to this. Anyway, guys. Any other questions you guys have? What about you guys? Do you have any more questions? No? You guys have questions? Hello? You have questions?
没写嘛，我就只会写 x 就除以它不得除以一个，然后这边要除以 n 个塔嘛，这约量的上面。什么时候写就是？假设它有所谓的同时这边是 n 个，它有 n 个 n 个，那就是n个平方。就是我这边不变的，所以它两个 n 是变的。
但我觉得这个太黑了，每天晚上做操就是做那个周六，然后做完之后流好多汗嘛，然后就看到汗都是紫色。
哎，头发。
做染头，然后之后流汗，然后都是黑的，黑紫黑紫。
你为什么拍的？
是吗？
你是直接按那个里面放那个色素？
对，那个是蓝的，但是特别黑，特别黑。
洗两次。
巨黑，就像那种我阿姨，然后那种两个傻黑的头。
染是先染下面，先染上面。
没有，就一块就染。就奶带。
我之前有
这个太大了，就是太变大了。
对，应该变大。
是不是？自己买的那个，特别便宜。我在 Wilco 买的，对，我在 Wilco 买的，好像1.2磅，2.3磅。
我怎么会想到？
它叫 Essence。它1楼就是收银台那边有一个就是卖化妆品的，然后那个好的直接有。
上去的时候不是看到了吗？
对，
咱们仨去的。
就是有卖那个。
他只要有让你看买些7加水。不对，不是我买指甲油是因为底油量有7加水。
对，我就直接抹了。
那怎么那个呢？自然的，你不能忍，所以我带来的那个指甲油是有可惜的。对啊。
哪有超多但是哪一瓶？而且我只要是刚用手来晒飞的是有相抗。但我不觉得很小。就这个，就这种。
Hello guys. Okay, guys. Any questions you guys have? I know some of you had questions. You still have questions? Yeah. You still have questions or what? Guys, you still have questions or what? No. Is it clear now? What about you guys? Is it clear? Okay, good. All right. So this is example. What example is it? Is it example 2, right? I did example 2, right? Which one was it? Let me see. Did I? Yeah, I just did example 2. So let me do another example. So this is example 2, okay? Now I'm going to do example 3 now. Oh, can you see this or not? So this is example 3. So we have, so in this example, the losses are IID exponential with parameter A, and you want to find the distributions of S, U, and V. They're the same. Okay, so let's start with S. So start with SA. We know that S is the sum of this, right? Now this is why you really need to know. I know some of you did my course last year, 2 years ago. It's called statistical methods. I taught in that course, I showed the class what the distribution of this is. Do you guys know the distribution of this? If x1 to xn are exponential, what distribution does the sum has? Yeah, good. Yeah, it's gamma. Very good. So it has this has a gamma distribution with parameters n and a. Okay. Okay. If you don't know, I mean, do you guys? All right. Let me write it down. Okay. I'll come back to that later. Okay. If you don't know what the gamma distribution is, you can look it up in the Wikipedia. All right. The CDF of S is wait a minute. This function is known as the incomplete. It's known as the incomplete gamma function. I'll get back to that later, but let me write down the PDF also. The PDF of S is the PDF is just simply the density of the gamma distribution, which is, I'm trying to remember what it is. It's gonna be, I think it's, correct me if I'm wrong, right, lumped up to the, is that right? Is this the density of the gamma distribution? Yes? I can't remember exactly. I think this is the correct. It may be, if this is, does somebody have the access to Wikipedia on the phone? I think, is this I'm trying to remember. Do you have the phone with you? Can you check the gamma distribution on the phone? That's wrong, guys. Sorry, I made a mistake. This should be A to the power n, and this should be S, not A. This should be S. It should be S, not A. Okay, can you change this to S? S to the power n minus 1. So the density, this is the density of the gamma distribution. is the parameters n and a. Okay. I apologize for this. The density of this is equal to this one. Okay. Now, as I said a minute ago, if you want to know the proof, I mean, I don't expect you to know the proof. If you want to know the proof that that the sum of independent, if you want to know the proof that this follows this distribution, you need to look up in the notes for statistical methods, which I taught 2 years ago, right? But once again, I don't expect you to know how to prove this, right? But if you want to know the proof, you can look up the notes, right? Okay. Okay, guys. Any questions so far? Yes. You should feel free to ask if you have any questions. Okay. So that's example 3. That's A. Now B. To do B, you need to know the CDF of U. The CDF of U is FU at U, which is 1 minus 1 minus okay, which is the 1 and the 1 cancels, so this would be okay, and the PDF of U is the derivative of this, which is okay, just this. Okay, and C. Are you okay? I mean, this is just to find the CDF. I'm using the formula that I derived earlier, right? Which if you want, I can show you to you again. This is the formula. You may recall this one. This is the formula I'm using to find this, right? And to find this, I'm using. This is just simply the derivative of this. So if you differentiate this with respect to U, this is what you will get. Okay. Now C. To find the CDF of V, right? I'm going to use the following formula, which is I showed you a minute ago. This is the formula, right? This is the formula I derived earlier for the CDF of V, right? So if I use this formula, you will get 1 minus E power n, right? Okay, and the PDF of V is just simply the derivative of this with respect to V. Alright, so it's gonna be A times this, okay? Right? Any questions so far, guys? So this is end of example 3. Yeah? Any questions? Sir, you okay? So so I derived. Just feel free to let me know if you have any questions. Just feel shout at me. I'm happy to go over this again. if you want me to, right? So I've done 3 examples. I hope that's enough. If you want more examples, I can do them later on. All right? Okay. Now the next thing I'm going to do, I only see there are 6 cases. When I started this lecture today, I told there are 6 different cases. I've only done one case so far. The next case is case 2, right? Case 2 is where, remember, the losses x1 to xn are IID, right, and n is random variable. Okay. Alright, that's case 2, right? So in this case, the CF of S, right? Is this, yeah? And this is do you know what this do you know something called the total probability rule? You must have done this like many years ago. Like that you can write here capital N denotes the number of investment, because now it's a variable, it's not a fixed number, right? Right? So you need to, so the probability that S is less than or equal to S can be written as the sum of this conditional probability. So this is the CDF of S conditioned on the number of investments being equal to little n times the probability that capital N equal to little n, right? Okay. Now, this is where we need to go back. We should go back to what we did earlier. Here we are. This is case 1. Okay. This is case 1, right? And we showed that the CDF of S is equal to this. This is the CDF of S. Now this assumes that the number of investments is fixed. So what you have here is the same as the conditional probability. Because in the conditional probability, we are assuming that the number of investment is fixed, right? So what I'm going to do is the following. I'm going to copy this. I'm going to copy this here and put it here, right? So what you will get is the following. You will get in place of the conditional probability, I'm going to put this guy here, right? Okay, so it will be integral So you see what I've done. This conditional probability, the probability of S given n equal to n is the same as what I wrote down here, right? Right. This is the conditional probability, right? Given capital N equal to n. So I put this thing here in place of this term here, right? Okay, and then you need to multiply this by the probability n equal to n, and then sum from 1 to infinity. So that's the answer. Okay. So that's the CDF of S. And do you have any questions, guys? Let me know. And the PDF of S is just simply the derivative, so it's right, this is the derivative. Okay? Yeah? Are you okay? That's okay? Okay, good. Alright, so this is case 2. Now, before I go ahead, I'm going to do the same example I did earlier. You may recall that this is the example I did a while ago, example 1, with n equal to 2. We got the CDF of S to be equal to this, right? So let me do the same example. So this is going to be example 4. Example 4. So suppose n equal to 2. Okay, and the CDF of S is, sorry, in this case we can't assume n equal to 2. Sorry, this is wrong example. Sorry, we can't assume because n is no longer fixed, so you can't assume. You can't assume that. So this example is no longer valid. Right. So anyway, I can't. You have to leave it like this. Okay. So let's go back. Let's go back to where I was here. Because for case 2, as you know, n is a random variable, so you can't fix. You can't fix it, right? Okay. So part B is to find the CDF of U. Okay. The CDF of U is the this, yeah. Remember, U is the minimum portfolio loss. This is once again I have used once again the total probability rule. Okay. All right. Now I'm going to show you what to do. I'm going to show you that if you look at what we did earlier, right here, in case 1, we showed that in case 1 that the CDF of U is given by this formula here, right? So what I'm going to do is I'm going to, in place of the conditional probability, I'm going to substitute this. So in place of this, I will sub this in, right? Okay. So this will be do you see what I've done? Because this is a conditional probability, n is fixed, right? The number of investments is fixed. So we can use that formula and put it here, okay? Okay, so this will be, this you can write as now, can somebody tell me what the first sum is? What's this equal to? This thing here equals to what? It's equal to 1, right? Because it's a sum of all probabilities, so it must be 1. So it's 1 . Alright. So this is the formula for the CDF of U under case 2, right? Okay. Alright, now the next is the PDF. The PDF of U is simply the derivative of this with respect to U, right? So you should take the derivative. Okay, you should differentiate this with respect to U, guys. This is what you will get. You will get sum from 1 to infinity of n minus 1 okay. Alright guys, you okay? So that's the PDF of U. Okay, any questions so far? Okay, now this is done. The next thing we need to do is to find V, right, which is the maximum portfolio loss. So this is C, okay. Okay, once again, this rule here follows by the total probability rule. Okay. Right, now to find the conditional probability, I'm going to use what we got under case 1. You may remember that in case 1, this is what we got. This is the formula that we got under case 1 for the CDF of V, right? Okay, so this is the same as the conditional probability. Okay, so this will be equal to okay, you follow me? Yeah. Okay, so this is the CDF of V. Now the PDF of V is this, right? So all you need to do is just differentiate this with respect to V. You will get the following. You will get sum from 1 to infinity of n n minus 1 okay, so this is it. Okay guys, any questions so far? So this is case 2. So we're done case 2 now. I will do some examples in a minute. Although we only have 5 minutes left, I will try to do some examples. Okay. Now, any question before I do examples? Do you have any questions on this? Everything clear? No, no. You okay, no? You okay? Yeah. Okay. Now, let me do, if I have time, let me do an example. Okay, this is example 4. Okay. Right. So here you have you have losses. This is clearly under case number 2. Okay, you have IID losses, but the number of investments is geometrically distributed with parameter A, and we want to find the distributions of U and V, right? Okay, so let's start with the CDF of U first. Now, if you use the formula that I just mentioned, where is it? This is the formula. This is the formula for the CDF of U, right? So the CDF of U is given by F now. What's the geometric? The probability n equal to n is what? It will be a times 1 minus a to the power n minus 1. Okay? Are you guys with me? This is the density function of the geometric distribution, right? I'm using this formula here. So this will be I'm going to pull out the A, and I'm going to pull out this. Then you have the sum from 1 to infinity of like this. Do you see what I've done? Then I'm going to make a substitution, set n equal to n minus 1. Okay, you should do the substitution. You get 1 minus a now. Under this substitution, the sum will go from where to where? It will go from 0 to infinity of right? Now, do you recognize this sum here, guys? What kind of summation is this? This one here. Do you know I'm sure you know the summation. It's known as what? Huh? It's the geometric sum. I'm sure. It's the geometric summation. Yeah. Did I not tell you this before? Or maybe let me write it down in case you don't know. You should have something like m from 0 to infinity of z power m. That's the same as 1 divided by 1 minus z. This is known as the geometric series. This is known as the geometric series, right? So this will be, so the answer is 1 minus a times 1 minus fxu, right, divided by 1 minus so this is the CDF of U, guys. Okay, and you can differentiate this to find the PDF of U. Is this clear so far? Yes. If it's not clear, let me know, guys. And so that's the CDF of U. I know we are running out of time. We already run out of time, but the next one is the CDF of V. The CDF of V is, if you use the formula that I gave you before, is n from 1 to infinity of fxv power n times the density of the geometric, which is this one, right? Now this you can pull out. You can pull out the a, you can pull out the fxv, and then inside you have 1 to infinity of fxv power n minus 1, 1 minus a power n minus 1, and then you make the substitution that m equal to n minus 1. If you make this substitution, you will get a times fxv, m from 0 to infinity of fxv 1 minus a, everything power m. Then finally, if you use the geometric sum, that is the sum from 0 to infinity of z power m is 1 divided by 1 minus z. If you use this geometric sum, this will reduce to the following. It will reduce to a fxv divided by 1 minus fxv times 1 minus a. Okay, so that's example 4, guys. Okay, tomorrow we will do more examples. And so is this any questions on this so far, guys? Let me know. Yeah, you guys okay? Yeah, I will try to do more examples tomorrow. I will, and then move on to case 3. So far we've done case 1 and 2. So we have 4 more cases left. Yeah. Yeah. All right, guys. Have a good night.